So recall that we're going to start the course by talking about spectroscopy, which is the study of the interaction of light with matter. We want to do this because as chemists, we're deeply interested in matter, right? We are set out to understand its properties and how it undergoes change. And so spectroscopy, let's go ahead and get that definition on here again. It's the study of the interaction of light with matter. Okay, so to really understand spectroscopy, we have to look a lot at light, the properties of light. So light is electromagnetic radiation. And we could get into a lot of depth into this if we wanted to, but we don't have the time. So this is going to be kind of like a mini version of Physics 2. I'll talk about the things we need to know in more detail and leave the other things like what does it mean to propagate an electronic and magnetic wave? What does it mean to be a wave? We'll talk about what we need to talk about, is my point. So light is made up of a collection of particles called photons. Okay, that's an important word. So photons have really interesting properties. First of all, let's just re-emphasize this. They're particles of light. They are massless, which is already itself interesting. They move at the speed of light within a vacuum. And they have variable energy. All of these are very important for just the universe, existing in the universe, but it's that last property that's particularly important for those interested in studying spectroscopy. That is, if they have variable energy, with variable energy, this is going to sound a little bit redundant, photons can have different energies. Can have different energies, and we'll appreciate that a lot more readily as we go through the content for this module. So let me start by let's draw a photon, and it's hard to think about what a photon looks like, but if it's a particle, I like to think of it as a sphere, and you're like, well, isn't light like a wave and a particle with a duality? Sure. But we're going to try to understand what we need to understand. And so I'm going to further reduce this away from physical reality by having some sort of face attached to it. I'm just going to call this my low energy photon. Now, what do we know about this low energy photon? First of all, we know that it's massless and it moves at the speed of light. We call the speed of light c because it's sort of a universal constant. Now, this photon with its sort of blah or meh face is different than, I don't know, how we draw a photon with a little bit more energy. It could have some emotion attached to it. Maybe it's some wild lines hanging off it. I don't know. What do we know about this photon? It is also massless, and it also moves at c, right? If it in a vacuum, those two things remain true, but now we say that this photon is high in energy. And I think there's something deep to appreciate here, and that is that if photons can have different energy, we could have one photon over here that's low energy, one photon over here that's high energy, and these photons are different. Okay, it's just important to realize that even though all light is massless and all light is moving at the speed of light within a vacuum, they can have different energies, and so some lights can be different. So if I say the phrase different lights, I'm sort of referring to different energies of light. Okay, so let's look at some examples of the various types of light. Again, if light can be different, we have high energy light, but let's focus on the photon. So high energy photons. Examples of these would be gamma and X-ray radiation. We consider these to be high energy forms of light. And already maybe you have a baseline for what a high energy photon can do. So in these cases, we can penetrate tissue quite dramatically in some instances, just to give you a baseline of what these things can do, right? We don't want to expose ourselves to too much X-ray radiation, and we want to expose ourselves to very minimal gamma radiation over our lifetimes. There is medium energy light or medium energy photons, and we call these ultraviolet or visible radiation. So ultraviolet and visible radiation, and we should be pretty familiar with this light. We can see visible radiation. We can detect it with our eyes and transmit signals to our brains and process information that way. Ultraviolet we cannot see, but we understand probably, or can have at least experienced its effects. It's higher energy than visible light, and it's sufficiently high energy that it can cause some damage to the surface tissue on our skin, leading to skin burns, or sunburns, excuse me. Okay, so we have high, medium, and low energy, and the thresholds aren't so important, just so you're kind of getting comfortable with seeing photons of various energies and appreciating where they're at in everyday life. So some low energy photon examples would be radio waves, microwaves, and IR, or infrared. So IR is used in IR spectroscopy. It's basically heat light or thermal light. And so this is now minimally damaging in and of itself, right? We can heat ourselves up too hot if we want to cause tissue damage that way, but it's not like just shining an IR beam at us will necessarily cause as much damage as the corresponding gamma beam would. Now, microwaves, obviously we can cook some food due to rotational excitation is what it's called, but microwaves aren't as bad again as gamma rays and that sort of thing. And exposing yourselves to self to microwaves won't cause a sunburn, for example, or some sort of skin damage that way. And radio waves are very innocuous or inert, or don't cause that much damage. Now, I really like to highlight this because radio waves are the source of radiation that we use in NMR spectroscopy. And what I want to emphasize continually is the use of radio waves is a huge advantage for NMR spectroscopy for understanding the properties, the chemical environment of nuclei within matter. Now, what's cool about it is we're going to spend a lot of time looking at how we can use those radio waves to understand the structure of organic molecules, which is a principal a driving force for this unit. And NMR really is one of the most powerful analytical techniques for determining the structure. But additionally, we can use these same properties within a living organism to image certain parts of a living organism without actually dissecting or penetrating the tissue physically. So we can use radiation to penetrate tissue. Now, the radiation, because it's radio waves, it doesn't cause as much damage as the penetrating radiation of X-ray radiation. So anyway, X-ray is a way to visualize inside of something, but radio waves can be used in a similar technique to NMR spectroscopy called MRI. So MRIs actually use radio waves, and MRIs are then incredibly safe compared to you know, X-ray techniques and that sort of thing. Okay, so as I mentioned, we're going to use radio waves in NMR spectroscopy. So I can clarify the definition of NMR spectroscopy a bit. So this looks at, NMR spectroscopy looks at how radio waves interact with matter inside, what's cool about this is inside a magnetic field. And this technique, I realize I just introduced magnetic field seemingly out of nowhere, but I just want to emphasize that this provides information about the chemical environment around an atom. And it's an atom with a particular nucleus. So it's not every atom necessarily. You have to tune the NMR spectroscopy instrumentation for a particular nucleus, like 1H, the hydrogen isotope with 0 neutrons, carbon 13, fluorine 19, and phosphorus 31, and importantly, N15. So these are just examples of different nuclei that you can use, that you can study using NMR spectroscopy. And what's that thing that we're studying? Once again, that's the chemical environment of the matter that we're looking at. So I'll highlight that. We have to keep using that word chemical environment. That's important. Okay, so what, oops, sorry, I just killed my recording here. Oh, just killed my share. Okay, so something else that's important here is looking at the various, well, let's just take a second and we'll just look at the different types of NMR spectroscopy techniques, which differ based on the nucleus that you're looking at. So what about C13 Nmr? Okay, so this is a special or a particular NMR technique focused on the chemical environment of carbon 13. Okay, now carbon 13 is the same as C13 this way, which has 6 protons, because all carbon atoms have 6 protons, and 7 neutrons. 6 protons and 7 neutrons. So we have carbon 13 written this way. Now, what about carbon 12? Carbon 12 is a great element. The majority of carbon in the universe is carbon 12. So why don't we study that? But what about carbon 12? The issue is that carbon 12, or C12 written this way, is not Nmr active. That is, it does not interact with radio waves like we would want so that we could detect signal using our NMR spectroscopy instrumentation. And there's a physical reason for this. We're not going to go into it right now, but it just turns out that if you put carbon 12 into an NMR instrument, the instrument can't learn anything about the carbon 12. It can't image anything about the carbon 12. That's kind of a problem because if carbon-12 is not NMR active, but it's the most abundant isotope of carbon, that means that the experiment we can run, carbon-13, is not highly sensitive. Okay, it's not highly sensitive, and that means it's difficult to achieve good signal. Now, what am I saying here? Well, if we put carbon into an instrument, and you would think in this class, organic chemistry, we would want to put carbon into the instrument if we're going to learn something about organic molecules. We're not going to see very big signals because the majority of those carbon atoms are, and it's really is not the most abundant, is not highly sensitive. You could write that here. C13 is approximately 1% of all carbons. So when we put that sample into the instrument, we're not going to see that big of a signal because there's not enough NMR active nuclei around to make a big signal, right? Okay, so the majority of it's carbon-12, 1% of all of those atoms will be carbon-13, okay, just statistically speaking. So we're not going to see big signals, which creates an important or a sort of problem that we have to deal with. So instead, what we need to focus on is NMR active nuclei. So more abundant NMR active nuclei. Well, not nitrogen. Nitrogen can be studied, but only as its N15 isotope. Not nitrogen, because N15 is active. We'll write that here. But not abundant. Okay, so what that means is you actually have to figure out a way, if you want to study nitrogen NMR, the best way to do it is to actually introduce nitrogen 15 using radio labeling techniques. Okay, getting into some, not so much some nuclear chemistry, but like buying radio labeled sources of fundamental feedstocks. This is really important for protein chemistry, by the way. Okay, now it's more abundant, some more abundant nuclei, well, not nitrogen, but if we think about phosphorus, phosphorus does have a good signal because its 31p isotope is both abundant and active. Both isotope abundant, I should write this here, and NMR active. Another example would be fluorine. If you have any fluorine in your molecule, you will see a big peak in the NMR spectrum because 19-fluorine is active, is very active, it turns out, very NMR active, and an abundant isotope. Okay, now the problem with 31p and 19F is it's not often the case, but it's unusual, I think it's fair to say. Not that these molecules aren't helpful and useful in themselves, but they're just unusual to have molecules have any phosphorus or fluorine in our molecules. What else? What other elements are NMR active and highly abundant could we study? Well, the king of all of this, and we're going to spend a lot of time on going forward, is the 1H atom. Is very NMR active, highly abundant, right? It's the most abundant isotope of hydrogen, and present in large amounts in most molecules. Like if you think back to all the molecules you had to draw in organic chemistry 1, how many of them had hydrogen? Like all of them, right? I mean, how often did we draw a molecule that was considered maybe an organic molecule that didn't have hydrogen? Like maybe CO2, but I don't think organic chemists or inorganic chemists can really claim CO2. It's that important, okay? Now, additionally, the other thing that makes this really cool is that if hydrogen is the king because it's so prominent, it's NMR active, and it's an abundant isotope, the other thing that makes it so cool is it's also present in water. So now not only are we restricted to what organic chemists need to do, but we can look at water. If we can look at the chemical environment of water, we can actually study biological processes at kind of a tissue and organ scale, and that's what we do with MRI technology. So NMR is nuclear magnetic resonance. MRI is magnetic resonance imaging. And MRI does the exact same thing that NMR does. It's the exact same technology, except instead of having to fit a tube with a little bit of organic molecules, you have to like fit a person. So you have to engineer a different instrument. But magnetic resonance imaging is NMR focused on water. And what about the water? It's the 1H atoms in the water. It uses the exact same technology engineered to look at things and report data differently so that we can, figure out what's going on with somebody's spleen or something without having to cut them open. So really great technology, and just hugely important, but also just same. We even though NMR, we may not use that acronym almost at all. It's we should be at least familiar with this technology, because whether or not you want to be a chemist, it's everywhere in the case of MRI technology. Okay, that'll do it for this lecture. We'll pick up with absorption spectroscopy next.